Welcome to the Problemos channel Season 2 Episode 13, the episode which I titled Blind Mathematical Justice, because in this episode we will discuss the solution of the mathematical problem S2E13, in which we are asked to generate a non-adaptive solution of a fake coin detection problem. And as we explained this in the previous episode, in each and every non-adaptive solution of a fake coin detection problem, we do not really look at the specific outcome of a specific weighing, and we do not really care about these outcomes. We only care about the overall outcome of the entire weighing experiment. And as authors of a non-adaptive solution of a fake coin detection problem, we can even write down this solution as a set of instructions ahead of time before the first weighing commences. We can give this recipe to a person who literally does not know what he or she is doing. We can walk out of the room, wait for the entire experiment to be over, walk back into the room, look at the result of the experiment, and announce to the world with absolute certainty the identity and, if needed, the weight quality of the fake coin. Before we do that, however, as a traditional friendly reminder, if you're joining our channel mid-season, then first of all, thank you very much and welcome to our channel. And second of all, it is a good idea for you to go to the homepage of this channel and in the channel's trailer section, find the episode titled The Problemos Channel How To, and watch that episode in its entirety and follow all the instructions given in that episode, because in that episode we explain and motivate everything that we do on this channel. In the mathematical problem S2E13, we're given 18 visually indistinguishable coins. We're told that precisely one coin out of these 18 is fake, and it is known ahead of time that that fake coin weighs detectably more than a genuine coin, which is to say that such a fake coin is heavy. And the challenge in this problem is to invent a non-adaptive solution which will allow us to determine the identity of the fake and heavy coin with absolute certainty. For comparison, in the previous episode, we managed to invent an adaptive solution of the 12-coin problem, and that solution, represented visually, looked as follows. And the reason such a solution is called adaptive is because in such a solution we not only look at each specific weighing as it unfolds, but we care very much about the outcome of each specific weighing, because as is evident by the graphical representation of such an adaptive solution, if, for example, the left pen goes down in this specific weighing, we do one thing. If the right pen goes down, then in this specific weighing, we do the other thing for the next weighing. And if the pens balance, then we take another action for the next weighing and distribute the coins over the pens and over the table in a way which adapts, or in a way looks at or cares a lot about the outcome of the previous weighing, and hence, in some sense, the title of the previous episode, Not Blind Mathematical Justice. In contrast, in this solution, we are expected to produce a way to detect the identity of the fake coin with absolute certainty, in a way in which we do not really look at the result of each weighing. Of course, we need to record it, but we do not care about what that result is, and we do not take any adaptive action depending on the result of this outcome. In other words, in this solution, we're expected to produce a description of that solution ahead of time before even the first weighing commences. Because we do not really know what is going on over here, and we generally do not have an idea of how to come up with such a non-adaptive solution of a fake coin detection problem, we begin attacking that problem in a way that is already familiar to our audience, and we begin looking at the fake coin detection problems that tilt the playing field, so to speak, in our favor as much as possible, because we want to start with cases which are straightforward and which we can understand what is going on in these cases and how to deal with them. In other words, we begin solving the fake coin detection problems in which the number of coins is a perfect power of 3 and in which the weight quality of the fake coin is known ahead of time. And for demonstration purposes throughout this episode, that fake coin will be heavy, and as such we begin our attack on the problem S2E13 with the standard 3 coin problem. For the duration of this episode, for demonstration purposes, let us agree that when I say the words a standard fake coin detection problem, that means that the number of coins in such a problem is a perfect power of 3, and that the weight quality of the fake coin in such a problem is known ahead of time. That fake coin can be heavy or that fake coin can be light. It doesn't really matter. Fundamentally and essentially, it makes absolutely no difference. But for demonstration purposes, again, for the duration of this episode, we will take it that the fake coin is heavy or weighs detectably more than a genuine coin. In the previous episode, we already generated an adaptive solution of this standard 3 coin problem. And in your upper right corner, I represented such an adaptive solution with a structure known as a ternary tree. And that is one happy idea that may lead us to the miniature discovery of how to generate a non-adaptive solution of a fake coin detection problem. And we already understand how that structure comes about. We depict graphically or visually the outcome of each weighing, and we know that on a properly functioning set of pen scales, there are possible only 3 outcomes, and consequently in one such weighing we cannot do better than producing 3 units of information. That is, in the standard 3 coin problem, we place one heavy suspect named H1, for example, on the left pen. We place the suspect named H2 on the right pen. We leave the remaining suspect H3 on the table. We perform precisely one weighing, and we know that as a result of such a weighing, only 3 outcomes are possible. The left pen goes down, the right pen goes down, or the pens balance. And precisely because the weight quality of the fake coin is known ahead of time, this is a standard problem. We see that if the left pen went down as a result of the first weighing, then with absolute certainty we know that the fake coin is H1 and it is heavy. If the right pen went down as depicted with this red edge over here, then with absolute certainty we know that the identity of the fake coin is H2 and that coin is heavy. And if the pens balance, which is represented by a vertical blue edge in this graph over here, then we know with absolute certainty that the identity of the fake coin is H3. Now, in some sense, a non-adaptive solution of this fake coin detection problem is already staring us in the face with this graph right here. But the way in which the solution of technical problems and problems in mathematics work is that in real time, in the instance of now, nothing is obvious, nothing is easy, nothing is straightforward and evident. Everything requires an effort. And for example, in the early days of what we now refer to as the theory of groups, the mathematicians who worked with the groups back in that time thought that only permutations or finite permutations could be the elements of a group. And again, in real time, it took people several years to realize that that is not the case. And as a matter of fact, it was the British mathematician by the name Arthur Cayley who came up with this awesome fundamental and a breathtaking, in some sense, idea that literally just about anything can participate in the formation of a group, and the only thing that matters in that process of formation of a group is the binary operation that governs the interaction between the elements of the future candidate group. Again, compare several minutes or hours that we may spend over here looking at a problem and several years of a real-time effort of the instance of now that was made by very bright people, and back then it was difficult and not obvious at all. These days, the students of mathematics, when they pick up a typical textbook on modern algebra or on the theory of groups, they look at a definition of a group and, oh my God, of course this is obvious. What else could it be? So here, if you are able to see what is going on and you can solve this problem completely and on your own correctly, then you can skip forward. But if that information presented over here is not enough, then we move on from the standard 3-coin problem to a standard 9-coin problem. As we step from the standard 3-coin problem to the standard 9-coin problem, we see that while the amount of information that we need to produce in the larger 9-coin problem also grows and becomes larger with respect to the amount of information that we had to produce in the smaller 3-coin problem. Fundamentally or essentially, the mechanics of the manufacturing of an adaptive solution of the standard 9-coin problem does not really change at all. That is, in the standard 9-coin problem, we need to produce 9 units of information, 1 unit of information for each distinct coin, and we know that on a single set of properly functioning pen scales with 1 weighing, we can produce no more than 3 units of information. Consequently, in 2 such consecutive weighings, we cannot produce more than 3 squared or 9 units of information. We have the need to produce 9 units of information here. We have the ability to do so theoretically. In other words, there is no hard theoretical barrier for an adaptive solution of such a problem, and we already know how to generate such an adaptive solution. We trisect the number of coins for the first weighing, and we put, for example, the first group of 3, the coins named H1, H2, H3, on the left pen. We put the next 3 coins named, for example, H4, H5, and H6 on the right pen, and we keep the remaining 3 coins named H7, H8, and H9 on the table. We perform the first weighing, and then regardless of the outcome of that weighing, whether as a result of that weighing the left pen goes down or the right pen goes down or the pens balance, we will have left precisely 3 suspects which we need to sort out during the second weighing, and that is when we do that. And notice how beautifully the second weighing in the 9-coin problem, shown over here, here, and here, represents a miniature instance of a previously smaller solved problem, or the 3-coin problem. In other words, for example, if as a result of the first weighing of this 9-coin problem the left pen went down, then the suspects over here with absolute certainty are the coins named H1, H2, H3, and we already know how to solve that smaller problem. That solution is represented over here. That solution is adaptive, and it is represented as a ternary tree, and that is exactly what we have over here. Likewise, if the right pen goes down, then we know with absolute certainty that the fake coin must be among the group of these 3 coins, H4, H5, H6, and the solution of that 3-coin problem is represented over here with the miniature tree that is a copy, faithful copy of this 3-coin tree. Here we have the suspects again, H4, H5, and H6, which sits out that second solution on the table. And if in the pens balance, then we know with absolute certainty that the fake coin must be one in the group of 3 coins that was on the table. Consequently, we put, for example, the coin named H7 on the left pen, we put the coin named H8 on the right pen, we keep the coin named H9 on the table, and we already know how to handle the rest. I will not go into the details. I will say only one thing, that I rotated the traditional ternary tree graph that we portray this way 90 degrees in order to save the space that we will need for the next experiment. At this point, again, we have plenty of material that we may need in order to discover how to generate a non-adaptive solution of this fake coin detection problem. But if you understood how we generated an adaptive solution of the three-coin problem and how we represented that adaptive solution with a structure known as ternary tree, and you were not able to solve the problem on your own and completely by yourself, then we suggest that you try to understand how we generated this adaptive solution of the 9-coin problem and how we represented that adaptive solution with another instance of a ternary tree. And if that analysis is also not enough, then you may take on the process of generating an adaptive solution of the 27-coin problem. Recall that no solution of any worthy mathematical problem pops out of nowhere and comes to us in vacuum. Conversely, any solution of any worthy mathematical problem only comes through our personal effort, and in order to generate such a solution, we have, parabolically speaking, step into the ring, cross the blades with the pirate, and get to know that problem up close and personal and generate the relevant and the needed details in order to solve the problem at hand. And the very process of generating the adaptive solutions of the 3 and the 9-coin problems and the process of representing these adaptive solutions with the corresponding ternary trees is exactly that up close and personal work with the problem that may help us discover a way in which we can produce a non-adaptive solution of a fake coin detection problem. If working with the corresponding 3 and 9 coin problems was not enough, then it is a good idea to generate an adaptive solution of a standard 27 coin problem and represent that solution with a ternary tree. Do not be lazy. Graph that tree or construct the tree in its entirety. This is what I have done over here, with the only exception that because that solution tree requires quite a bit of space and I don't have much of it, I dropped the designation for the suspect fake coin as an uppercase letter H for heavy, and I simply use the numbers or the subscripts of these coins. In other words, with the standard 27 coin problem, we have again 27 visually indistinguishable coins. Precisely one is fake. The weight quality of that fake coin is known ahead of time. It weighs detectably more than a genuine coin. That fake coin is heavy. We number the coins 1 through 27, and in order to generate an adaptive solution of the standard 27 coin problem, again we trisect or divide in 3 equal parts all the coins. We put the first group of 9 coins, in this case, on one pen. Here I represented these coins with the numbers 1 through 9. We put the next group of 9 coins, in this case and for demonstration purposes numbered 10 through 18, on the right pen, and we keep the remaining 9 coins named 19 and so on through 27 on the table. And again, in this problem we need to generate 27 units of information. We know that theoretically, with each weighing on a properly functioning set of pen scales, we can not do better than 3 units of information. Consequently, 3 raised to the 3rd power gives us 27. So theoretically, we can produce 27 units of information. So it looks like there is no hard theoretical barrier for an adaptive solution of this problem. And as we see, that is precisely the case. We can generate such an adaptive solution and represent it with a ternary tree. And again, observe how, as a result of the first weighing, we can have the fact that the left pen goes down or the right pen goes down, or the pens balance as represented by this green edge over here. And for the second weighing, this one, and this one, what do we have? Again, we have a beautiful reduction of the current larger and more complicated problem to a previously solved smaller, in some sense, and in some sense simpler problem of the 9 coins. In other words, if the left pen, as a result of the first weighing over here, goes down, then we know with absolute certainty that the fake coin is amongst the 9 coins numbered 1 through 9. And as a second weighing, what do we have? Well, we have a graphical representation of a previously solved problem. In other words, we take the ternary tree that we produced in the solution of the 9 coin problem, compress it a little bit, and we slug it in over here, and we know how to deal with this group of 9 coins over here. If the right pen goes down as a result of the first weighing here, we have another group of 9 coins as a definite suspect group. We know with absolute certainty that the fake coin is amongst the coins numbered 10 through 11. And as the second weighing over here, again, we have a group of 9 coins. They are numbered differently, but still we know how to solve this problem, because for the problem we simply take the ternary tree that we generated in the previous simpler or smaller problem, slug it into here, and the problem is solved. Likewise, if the pens as a result of the first weighing do balance as represented by this green edge over here, we know with absolute certainty that the fake coin is one amongst the coins that were on the table. These coins are not named 19 through 27. Still, this is 9 coins, and we know how to solve that problem by using the solution of the previous 9 coin problem. Again, here we have plenty of information. At this point, I will not go and drill this problem any deeper, but in some sense, you may want to think about how to generate a solution of the standard 81 coin problem, but we will stop over here, and in the next segment, we will make the next step towards the discovery of a non-adaptive solution of the mathematical problem S2E13. Now that we have plenty of experimental material to work with, let us think together. Each and every object on the board represents a ternary tree, and a tree is a graph-theoretic object in which any two nodes are connected with precisely and exactly one path. And that means that over this tree, for example, there exists exactly and precisely one path from the node named, for example, 15 to the node, let's say, number 4. And what does this path look like? Well, we begin our journey at the node named 15, go up, then we go left, then we go down, then we go right, and then we go left, and we arrive at the node number 4. And conversely, of course, in the same way, we can trace our steps back and get from the node named number 4 to the node named number 15. But do these journeys or do these paths make any sense in our context, in the context of this fake coin detection problem? The answer is no, of course. Such paths do not make any sense, because what does this path, for example, from the node named 15 to the node named number 4 represent? Well, such a path represents the fact that we need to somehow undo the weighing number 3, then we have to undo the weighing number 2, then we have to undo the weighing number 1, and we have to reshuffle the whole experiment and start executing weighing number 1, weighing number 2, and weighing number 3. That the whole scenario doesn't make any sense in our problem, and that means that these types of paths are of no interest to us. What types of paths are of interest to us? Well, our experiment in some sense flows in one direction in time, from the weighing number 1 to any of the weighings number 2 captured in our ternary tree to any one of the weighings number 3. Consequently, the paths that are of interest to us over the respective ternary tree that faithfully represents an adaptive solution of this fake coin detection problem are the paths that originate at the root node of our ternary tree that represents the first weighing and that terminates at the leaf node of our ternary tree. And we understand that each and every intermediate node in such a potential path represents a specific weighing, and the exception to that rule are the leaf nodes in our ternary tree, where each and every specific leaf node, such as the node number 4, for example, represents a particular outcome or a solution in some sense of this fake coin detection problem, because such leaf node identifies with absolute certainty the name of the fake and heavy coin. So what kind of tactically useful or tactically fruitful conclusion can we make from that observation? Well, let's step back a little bit and look at the ternary tree shown over here, a ternary tree that is a faithful representation of an adaptive solution of the 27 coin problem. And what kind of conclusions can we make? Does that tree represent an adaptive solution of that problem faithfully? Yes, it does. Does that tree makes the consumption and comprehension of the whole solution easy and straightforward in some sense? Yes, it does. It is very easy in some sense and very straightforward to read that tree and figure out what the solution is. But let us also keep a sober attitude towards the size of the information that is needed to lay out that visual representation of the corresponding adaptive solution of this fake coin detection problem. It takes a lot of room, it takes a good chunk of this board, and in contrast, a non-adaptive solution of a fake coin detection problem supposed to be pretty compact. So is there a way to compress all that information that's shown on the board over here and make it very compact and small? And the answer to that question is yes. Several hundred years ago, a French mathematician, René Descartes, invented or discovered, depending on your stance, what we now know as analytic geometry by joining the synthetic geometry with the respective symbolic algebra. And from that moment onward, many, if not all, of our favorite curves gained two distinct definitions. One such definition came from the synthetic geometry, and another such definition came from the respective symbolic algebra. For example, on the one hand, a circle is a set of points in a fixed plane, each of which is equidistant from a given fixed point called the center of a circle. And on the other hand, an origin-centered circle became x squared plus y squared equals r squared. In our case, we do not really have much geometry to speak of, but we do have a visual representation and a faithful visual representation of an adaptive solution of a fake coin detection problem. So how can we introduce some meaningful symbolic algebra into the mix? Well, we do not have to be Carl Gauss and Leonhard Euler to realize that in order to introduce meaningful and fruitful symbolic algebra into our problem, all we have to do is compress the name of a pen that went down as a result of this specific weighing into just one letter. Because in our problem, the fake coin is heavy. If, on the other hand, we had a case where a fake coin is light, then with this specific letter, we would record the name of the pen that went up as a result of the respective weighing. In other words, here, if as a result of the first weighing, the left pen went down, we will capture that event with the uppercase letter L. If as a result of the first weighing, the right pen went down, then we will capture that event with the uppercase letter R. And if a result of the first weighing, the pens balanced, then we will capture that event with the letter B. And of course, here we should not get confused with the uppercase letter L, because in the previous episode we used the uppercase L to designate the candidate that was light or weight detectably less than a genuine coin. And here, again, just to make sure that we're all on the same page, the uppercase letter L represents the fact that as a result of a specific weighing, the left pen went down. Now, from our previous segment, we remember that to each and every specific coin represented by a leaf node in our ternary tree, there corresponds a unique path that originates at the root node of our ternary tree, rattles around the ternary tree, and terminates at this specific leaf node. And what does that mean further? Well, if it's not clear still where this is going, it is instructive to actually roll through the entire tree and write down the outcomes of all the weighings in our new notation. For example, here we will put the letter L again, here we will put the letter L, and we roll through all the tree for all the tree, entire tree, and designate the left outcome with the letter L, for example, like so, left, 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 another left, and another left. Then we do the same with the right pen going down. So here we will have the right pen went down, the right pen went down here, the right pen, right, another right, and so on. And then we do the same thing with the letter B, and we capture all the cases when the pens balance here. For example, here the letters will be somewhat small. I know you guys complain about the small size, but here I'll try to make the best of it. Here, this letter B, here another letter B, here is another, I'll write it on this side, letter B here. Where is another one? Here is another balance, and another balance. And what kind of conclusion do we make now? Well, we already observed that precisely because our object over here is called a ternary tree, we know what a tree is, we know what a path over a tree is, we know why this tree is called ternary, because each and every node in that tree has no more than 3 children. And we observed earlier that to each and every specific leaf node, there corresponds a unique path that originates at the root node of the tree, rattles around the tree, and terminates at that particular leaf node. And now that we assigned the letters L, R, B to each specific outcome of each specific weighing, what else can we state? What is the next conclusion that we can make? Well, the next conclusion that we make over here is that to each and every specific coin, or to each and every specific leaf node in our ternary tree, they corresponds a specific arrangement of the letters L, R, B. And for example, let us capture some of the sample arrangements. For example, for the coin number 4, what can we say? For the coin number 4, this such arrangement will be, for example, what is it? Left, right, and then left. So we will write left. I will keep track of the direction of the execution of the weighings right to left in this direction. So the first outcome is left, the next outcome is right, and the next outcome is left again. So I'll read it right to left, L, R, L. So let's pick another one just for kicks. Let's say number 11. To the coin named 11 and to the leaf node named 11 over here, what kind of arrangement of the letters LRB corresponds? Well, it's R, L, R. So it's R as the first one, the outcome of the first weighing, then it is L, and it is R again, and that is, what's the coin number? 11. That's the coin number 11. And let's do another one. For example, let's record the sequence of letters that terminate at the leaf node named 14. So for example, for the node named 14, what type of letters do we have? Right, right, right. So 3, as a matter of fact, I forgot to write it over here. Yes, right. So here we have right, right, and right. Now, what are these arrangements of the letters L, R? Well, we don't have, okay, let's do, for example, node 24 for demonstration purposes, just to have all the letters. To the node 24, what do we have? To the node 24, we have balance, then we have, again, right, and then we have balance. So it will be balance, then it will be right, then it will be balance again. So now we have the representations of all the letters. And what do these arrangements of letters, or the LRB paths, what are they called in mathematics? Well, again, you don't have to be a genius to realize that what we have here is the so-called 3 permutations with repetitions, where each and every item is available in an infinite supply. And the restriction clause that each and every item is available in infinite supply is a way in which mathematicians deal with the requirement that if and when we need an item of this specific type, we always have it, and we do not need to worry about keeping track of these items. And there are fairly deep set theoretic reasons for that. For example, if from an infinite set we remove any finite amount of items, then that set still remains infinite, and that is in stark contrast with finite sets. So how do these 3 permutations of 3 distinct items named L, R, B, each of which is available in an infinite supply, are constructed, and how many of them are possible? Well, how many, let's think about this together. How many candidates, or in how many ways can we fill out, for example, the first position in our path? Well, we can do it in 3 ways. And in general, if we have n distinct items, then we have n choices with which we can fill out the first position. So we'll write n over here. Now, regardless of a specific choice of a specific item which we put into the first position, how many choices do we have for the second position in our permutation? Well, this is where the infinite supply requirement comes in. We still have 3 choices for filling out the second position in our path. And that means that by multiplication counting principle, the total number of such 2 permutations in this case will be equal to 3 times 3, and in general, it will be n times n. Now, next, regardless of the specific choices that we made to fill out the first position in our path and the second position in our path, how many choices do we have for filling out the third position in our path? Well, again, because each and every item is available in an infinite supply, we still have three choices with which we can fill out the third position in our RLB path. And the total number of such 3 permutations with repetitions will be clearly given by 3 to the 3rd power. In this case, it works out to, we see, 27. In general, we will have, let's say, n distinct items sprinkled over k distinct positions, 1, 2, 3, and so on, and then the total number of k permutations with repetitions of n distinct items, each of which is available in an infinite supply, will be given by what? N to the power of k. Now we notice that each and every path over the ternary tree shown over here that originates at the root node of the tree and terminates at a specific coin, which represents a solution of this problem, has how many legs? Has precisely 3 legs, no matter which coin we pick as a solution or as a fake and heavy. Consequently, we will have each such unique path will correspond to a unique 3 permutation of 3 distinct items, LRB, with repetitions where each and every item is available in an infinite supply. So what can we say now about the correlation between the leaf nodes and the corresponding paths? Well, now we can say that to each specific leaf node in our tree, there corresponds a unique 3 permutation with repetitions of the letters L, R, B, each of which is available in an infinite supply. And usually when we make these statements, mathematicians want to say and conversely. But does and conversely work over here in this specific case? The answer to that question is yes. And conversely also works. In other words, to each specific coin, to each specific leaf node in our ternary tree, there corresponds a unique 3 permutation with repetitions of 3 distinct items L, R, B, each of which is available in an infinite supply. And conversely, to each and every specific 3 permutation with repetitions of 3 distinct items L, R, B, each of which available in an infinite supply, there corresponds a unique path over our ternary tree that originates at the root node of the tree, rattles around the tree, and terminates with a distinct coin, or terminates with a distinct leaf node of our tree. And in mathematics, this type of relationship between 2 sets is called a bijection. Such a relationship is injective and surjective, and hence bijective. And we understand that pretty much the only reason that we have a bijection between the coins in our problem and the corresponding LRB paths, to which we will refer as LRB paths from now on for brevity, is because the number of coins in the problem is a perfect power of 3 right here, a perfect power of 3, and the weight quality of the fake coin is known ahead of time. And in some way also notice that even though we started working with a problem that dealt with fake coins, here we see a little bit of a visual demonstration of how certain combinatorial objects work. And we see that because precisely the number of coins is a perfect power of 3, 27, when we construct all 27 3 permutations with repetitions of the letters L, R, and B, each of which is available in an infinite supply, we will precisely have, to each such permutation, we will be able to find the corresponding path over the tree that originates at the root node and terminates at the respective leaf node of the tree. And now the question is, what next fruitful conclusion can we make from all these observations. Well, we are pretty much done. First, observe that the three permutation with repetitions of the distinct letters L, R, B, each of which is available in an infinite supply that is associated with a specific coin, on the one hand, tells not only a story about that coin, but in some sense defines its fate as that coin bounces around the pins and percolates its way through the weighings of the entire experiment. On the other hand, that fate can be computed or defined ahead of time before even the first weighing begins. And that is exactly what we do. Essentially playing out one of our favorite computer science algorithms here by hand, which is a rapid fun. We construct all 27 three permutations of the letters LRB shown on your right over here, and to these permutations we assign the old names of the coins that we used prior to this experiment, such as 1, 2, 3, and so on. But very quickly we understand that these old names become absolutely useless and absolutely meaningless, because from that point onward the only thing that matters for us is a specific three permutation with repetition of the distinct letters LRB, because such a path becomes a sort of portrait of each coin, and the old name of the coin that we used can be thrown out. Next, we notice that the bottom row of the leaf nodes in our tertiary tree can be partitioned into three subsets. The subset of the coins named 1 through 9 that sit under the first left branch of our tree, shown over here, designated with the word left. We can also have another subset called right, and in that subset there sit all the coins named 10 through 18, and they live under the first right branch of the tree. And consequently, the subset called balance are the coins named 19 through 27 that sit under the first balanced branch of our tree. And what can we say about the subsets of these coins? Well, let's take, for example, the left subset. We see that in this subset of coins, all the coins named 1, 2, 3, 4, 5, 6, 7, 8, 9 that were placed on the left pen for the first weighing are present over here. None is missing. And at the same time, no other coin from the remaining subsets is located over here. And the same observation holds for the right subset. For example, in that subset, we see all the coins named 10 through 18. None of these coins is missing. No other coins in this subset can be seen. And these are all the coins that were placed on the right pin for the weighing number 1. And the same observation again can be made about the final subset called balance. Over here we have all the coins, none of them are missing, named 19 through 27, and no other coins from the other subsets can be seen over here. Now that idea can be applied recursively to other weighings, to weighing number 2. For example, let's concentrate on the subset of the subset on the left called 1, 3, and 2. Over here we have all the coins that were placed on the left pen for the second weighing, the coins named 1, 2, 3. And all these coins are over here, 1, 3, and 2. And no other coins are in that section over here. And again, the same idea applies to all the other subsets that can be distinguished once we analyze the second weighing, the weighing number 2. And once we drill it down over here on the last weighing, we of course already determine the fake coin with absolute certainty. So we know that coin number 1 has the letter L associated over here in that position, coin number 2 letter R, and coin number 3 letter B. And thus comes about the idea that in non-adaptive solution of this specific 27 coin problem can be the following one. We, like we said before, generate all 27 3 permutations with repetitions of the distinct letters L, R, B. We assign the old names to them if we have to in any way possible. It doesn't really matter. The assignment of the old names over here that I shown is just a sample one. It doesn't have to be that specific one. You can name these LRB paths in any which way you want, pick a different assignments. And then here is the important part. For the weighing number K, we pick all the coins that have the letter L in the kth position of their LRB path, and we put all these coins on the left pan. Likewise, we take all the coins that have the letter R in their kth position of their respective LRB path, and we put these coins on the right pan. Lastly, we take all the coins out of 27 that have the letter B in their kth position in their respective LRB path, and we keep these coins on the table. Then we ask someone to distribute, we distribute the coins in a way in which I will explain over here, but according to this algorithm, and we ask that person to conduct 3 weighings and in some sense blindly record the outcome of all 3 weighings, write them down on a piece of paper, give this paper to us, and our solution says that the outcome of the overall experiment names the fake coin with absolute certainty. In other words, the 3 letters that the person wrote down as a result of conducting all 3 weighings will be some combinations of the letters L, R, B, and that 3 permutation, that is the outcome of the entire experiment, will name the fake and heavy coin with absolute certainty, and we can find the old name of that coin using our translation table shown over here. And just to make sure that we're all on the same page and we all understand what is going on, a non-adaptive solution of this 27 coin problem looks essentially as follows. Here I wrote down the scenario, so to speak, or the set recipe that we were looking for that can be followed by a person who has absolutely no clue what he or she is doing, and we can solve the problem. In other words, for the weighing number 1 portrayed over here, on the left pan we put the coins named 1 through 9 precisely because in the LRB path of these coins the letter L shows up over here, and just to make sure I keep track of the direction first to last in the direction from right to left. This is just my arbitrary decision. Again, there is nothing fundamental over here. You can keep track of your direction in the opposite way. You can start counting from left and go to right, but the reason I pick my direction is because for almost 30 years I was mostly writing C and C++ code. In computer programming, the bits are numbered right to left, and this is just my choice. And we see that we place on the right pan for the weighing number 1 all the coins that are named 10 through 18, precisely because in the LRB paths of these coins, in the first position or the rightmost position in my counting, there sits which letter? Letter R. R, 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 and so on. 10 through 18 go on to the right pan. And what's left over? Well, what's left over are the coins named 19 through 27, and we already understand that in the first, or in my counting, rightmost position of the respective LRB paths of all these coins, there will be letter B, as shown over here, B, 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 and so on. We ask someone, once we put the coins that way, we ask someone to perform the measurement, record which way the pens went in this specific weighing, and then again, blindly, and that is why the title of this episode is Blind Mathematical Justice, blindly in the sense that we do not really care what the outcome of this specific weighing number one was, we just want to write it down. We put the coins for the second weighing also in a predetermined way as follows. On the left pan, there go all the coins that have the letter L in their second position of the respective LRB path. And in this case, this will be all the coins that sit in this horizontal band right here because they have letter L, 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 and L, L, L in the second position. So now we see that again, in case you guys cannot see it clearly, for the weighing number 2, on the left pan, there go coins named 1, 2, 3, 10, 11, 12, 19, 20, and 21. And again, we understand why, because in the second position of their respective LRB paths, there sits precisely the letter L. On the right pan, for the weighing number 2, will go all the coins that have the letter R in their second position of their respective LRB paths. And as you can see, all these coins will be in this narrow middle band right here in the horizontal band, because in the second position of the LRB paths of all these coins, there sits precisely the letter R. R, 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 letter R, 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 and the same thing over here. So these coins are 4, 5, 6, 13, 14, 15, 22, 23, 24. And this is precisely what I have on the right pan for weighing number 2. The coins named 4, 5, 6, 13, 14, 15, 22, 23, 24. And already we can do this by elimination. The remaining coins will be on the table, but just in case, we understand that for the second weighing, in the second position of their respective LRB paths, there should be which letter? The letter B. And precisely this is what happens over here in the horizontal band over here on the bottom. Letter B, B, and B sits over here in the second position of all the coins named with their old names. And these coins are 7, 8, 9, 16, 17, 18, 25, 26, and 27. So this distribution of coins and this description, just to make sure, again, is done ahead of time before even the first weighing commences. For the weighing number 3, this is when the instance of K is equal to 3. Which position in the respective LRB paths do we care about? The third position. Again, the way I count, that will be the leftmost position. If you count in a different direction, that will be the rightmost position. So which coins in our set have the letter L in their last position, position number 3, in my case, the leftmost position? Well, we just scan this table over here and count L, 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 what else? This guy, and this guy. So for the weighing number 3 on the left pan, because in the leftmost position, in the third position of the respective LRB paths of these coins, we have precisely the letter L. We have the coins named 1, 4, 7, 10, 13, 16, 19, 20, and 25. Next, for the weighing number 3, in the third or final position of the LRB paths of these coins, there will sit the letter R, and all these coins go onto the right pan, as shown with the blue line over here. And what are these coins? Well, again, we roll through our table quite mechanically and in some sense blindly, without really caring about what the outcome of weighing number 1 and weighing number 2 was. We compile this list of coins or distribution of coins ahead of time. And we take for the right pan, for the weighing number 3, the coins named 2, 5, 8, 11, 14, 17, 20, 23, and 26. And again, what will remain? What will remain are all the coins that have the letter B in their third, in my counting, leftmost position in the respective LRB paths of these coins. And again, for example, this will be coin named 3, 6, 9, 12, 15, 18, 21, 24, 27, and this is exactly what I have over here. In case you guys cannot see it and these numbers are small, I don't have much room. The coins named 3, 6, 9, 12, 15, 18, 21, 24, 27 go onto the table for the final weighing, for the weighing number 3. Again, someone can distribute these coins over the pans according to this recipe, which we compiled ahead of time, conduct all 3 weighings, write down the result of these outcomes, and because again, I read all my results in the right to left fashion. For example, let's say someone conducted this experiment and the pans went the following way. They balanced first, so this will be recorded with the letter B. Then the pans went right, the right pan went down, recorded with the letter R over here. And finally, on the third weighing, the left pan went down. And at the time when this experiment was performed, we were not even in the room. Someone wrote down these results, brought it to us. We'll look at this and say, BRL. We go back to our translation table and we find that path, BRL. Where is it? Well, let's see. Here it is, BRL. In our old names, that's the coin number 22. And we announce to the world with absolute certainty that the coin number 22 is fake and heavy, and that is the essence of a non-adaptive solution of this 27 coin problem. Again, it should be understood that the moment we hit upon this bright idea of encoding our coins with the LRB paths by writing these paths down with a mathematical or massless ink that doesn't alter the mass of each coin in any detectable way, then from that instance onward, the old names become absolutely irrelevant. Instead of my numbering over here 1, 2, 3, 4, 5, 6, 7, 8, 9, you can sprinkle any numbers, old numbers you like. You can put 24 here, you can put 2 here, crisscross any which way, it doesn't really matter, as long as the overall essence is understood. We construct all 27 3 permutations with repetitions of the distinct letters LRB, each of which is available in an infinite supply. In some arbitrary fashion, we assign the old names to these permutations. These permutations become the portraits or unique portraits of each coin, and that's the only thing we care about. And then for the kth weighing, we put all the coins that have the letter L in the kth position of their LRB path on the left pan. We put all the coins that have the letter R in the kth position of their respective LRB path on the right pan. The remaining coins go on the table, but just in case, all the coins that have the letter B in the kth position of their respective LRB path go onto the table. This distribution of coins is compiled ahead of time. It is given to a person who has absolutely no idea what he or she is doing. She blindly, in some sense, distributes the coins according to our recipe, writes down the outcome, and that outcome identifies the fake and heavy coin with absolute certainty. And again, just because I use the right to left direction to keep track of my results, it's just my arbitrary decision. You can pick any other direction. It will work as long as you are consistent with writing down the names which reflect the fate or reflect the bouncing of the coin left-right balance over the tree. And you, in agreement with that pick direction, read and interpret the outcome of the weighing. Now that we understand how a non-adaptive of this 27 coin problem works, we can take on the original problem that was given in this challenge and see how this can be done with 18 coins. It is interesting that sometimes in mathematics it is easier in some sense to solve a more general problem and then reduce the obtained solution of a more general problem to a solution of a slightly less general and more specific problem. And in our case, at first blush, it could seem that solving a 27 coin puzzle will be more difficult, but as we will understand fairly quickly, that is not the case, and that is why we attack that problem first. And once we understand how to solve a more general problem, the solution of a more specific and less general problem becomes more straightforward as well. So over here, when we are given 18 visually indistinguishable coins, one of them is fake and it's known to be heavy, we're asked to generate a non-adaptive solution of such a coin, which will allow us to identify the fake coin with absolute certainty. Given everything that we said already prior, we try to generate a adaptive solution of the 18 coin problem first, and we already understand how that works. Such a solution can be faithfully represented with a corresponding ternary tree that I depicted over here. I basically reused the previous tree that we used for the 27 coin problem, and again, it should be fairly evident that in this case we also trisect the number of coins. 18 is not a perfect power of 3, but luckily it is divisible by 3. So in this case we put the coins named 1 through 6 on the left pen for the weighing number 1. We put the coins named 7 through 12 on the right pen. We keep the coins named 13 through 18 on the table for the first weighing, and then if the left pen goes down, then we know that we have 6 suspects to deal with, and we deal with these suspects in this subtree. If the right pen goes down as the result of the first weighing, then we know how to deal with these 6 suspects named 7 through 12. If the pens balance, then we know that these 6 suspects 13 through 18 are it. They contain a fake coin, and we know how to deal with each problem where we need to identify the fake coin among 6. Also, already we understand how this can be done. For example, here in this case, we put the coins named 1 and 2 on the left pen. We put the coins named 3 and 4 on the right pen. We execute the weighing number 2. If the pens balance, then we know the coins 5 and 6 are the suspects, and the rest of them are control coins. If the left pen goes down, then we need to sort out the coins 1 and 2. If the right pen goes down, then we need to sort out the coins 3 and 4 as depicted over here. Everything is very nice. We understand how this works, and we step back. We look at the corresponding ternary tree, and what do we see about what specific feature of the structure of that tree do we see? Well, we see that in the way we laid it out, there are absolutely no balanced outcomes on the very last weighing over here. Again, you guys can see I didn't try even to do a very good job. On purpose, I left some of the marks, but you can see that I erased all the balanced outcomes for the third weighing. None of them are present. That already should tell us something. But again, the same idea of partitioning the bottom row or all the leaf nodes of this ternary tree into 3 distinct subsets. The subset of the coins that went down on the left pen, on the first left branch, the right branch, the balanced branch, the same ideas apply. We again construct ahead of time the corresponding LRB paths for all the coins, and I display these paths over here on your right. Again, on purpose, I did not do a very good job erasing what? Precisely, I did not do purposefully a good job of erasing all the LRB paths that had the letter B, as you can see over here. I left it here on purpose as well, the letter B in its leftmost or the third position, because I count my directions right to left. So all these guys are gone. 3, 3, and 3, 9, 27 minus 9, 18. We have our 18 coins. Again, these distributions that I put over here are for demonstration purposes. You can pick any which one you like. They have any significance whatsoever. The only thing that matters in the non-adaptive solution of fake coin detection problems are the encodings or the paths of the coins that we assign. And we see that, again, if we act in a sort of mechanical way without thinking too much, right now we'll understand that we're getting lucky. But in this case, when we assign the old names to the new 3 permutations of the letters L, R, B that are only possible in this case, we see that the bijection between the paths and the 3 permutations with repetitions evaporates. It's no longer there because we do not have all 27 coins. Some paths from our original complete tree are missing, and we see which ones are these, the ones that terminate with the balanced outcome over here. But still the same principle applies. For the weighing number 1, and these 3 lines over here constitute the very non-adaptive solution that we were looking for the problem S2E13. We write all these numbers down ahead of time before even the first weighing commences. We give this list of distributions of the coins over the pens to the person who has no idea what he or she is doing. We tell them what needs to be done. They record the result, bring it back to us, and we say, LRB or XYZ. Boom, this is the fake coin. And the distribution over here is follows. For the weighing number 1, the coins named 1 through 6 go onto the left pen. Why? Because all these coins have the letter L in their first position of their respective LRB paths. The coins named 7 through 12 go onto the right pen over here because they have the letter R in the first position of their respective LRB paths, 7 through 12. The coins named 13 through 18 remain on the table because they have the letter B in the first or rightmost position in their respective LRB paths. The person who conducts this experiment distributes the coins this way without even understanding why he or she is doing it. She just does it, records the results. Then that person will shuffle the coins for the second weighing as follows. The coins named 1, 2, 7, 8, 13, 14 go onto the left pen. We understand why, because in these coins, what was it? 1, 2, 7, 8. Again, in the horizontal band, we have letter L in the second position here, 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 here. So we have our 1, 2, 7, 8, 13, 14. For the second weighing, for the weighing number 2, all the coins named 3, 4, 9, 10, 15, 16 go onto the right band. We understand why. These are all the coins from the middle horizontal band, precisely because in the second position, for the weighing number 2, they have the letter R in their second position, 3, 4, 9, 10, 15, 16. These are the guys shown over here. The remaining coins named 5, 6, 11, 12, 17, 18 sit out that weighing number 2 on the table. Why? Because they have the letter B in the second position in their respective LRB paths that are captured over here in the bottom horizontal band. And again, the person who conducts this experiment distributes the coins this way, executes the weighings, observes the result, writes it down. Everyone is happy. And for the final weighing, for the weighing number 3, that person shuffles the coins as follows. The coins named 1, 3, 5, 7, 9, 11, 13, 15, 17, basically all the odd numbered coins go onto the left pan, because again, it so happens we threw out all the paths that have the letter B in the leftmost path, and these are the coins over here: 1, 3, 5, 7, 9, and so on. And because the number of coins is even in our case, we have, I forgot to underscore this guy with the blue, the coins shown over here go onto the right pan, all the even numbered coins, 2, 4, 6, 8, 10, 12, 14, 16, 18, precisely because all these coins have the letter R in their third position in the respective LRB paths over here, 2, 4, 6, 8, 10, and so on. the person conducts the third weighing. Here I use the hijack the symbol for the empty set for the coins that will be on the table. There are no coins in the table. Again, in this problem, there may be different ways to proceed. This is just one way. And notice that in the first two weighings, we put 6 coins per pen here and here, and here and here. But for the third weighing, because we did not have the balanced outcome anywhere in the structure of the corresponding ternary tree that we constructed based on an adaptive solution, we put 9 coins on the left pen, 9 coins on the right pen, 9 plus 9, 18. No coins go on the table, and that schedule, or that recipe, if you will, represents the very non-adaptive solution of the 18 coin problem that we sought after. However, as we shuffle our coins and construct these non-adaptive solutions of the fake coin detection problem, we understand that in some way we've got lucky, because over here with 18 coins, 18 is not a perfect power of 3, we did not have the nice bijection between the all possible paths and the 3 permutations with repetitions of the letters L, R, and B, but still fairly mechanically, and perhaps, with some amount of luck, we were able to convert an adaptive solution of this fake coin detection problem into a non-adaptive solution of a fake coin detection problem. But as we work more and more with more cases, especially with the cases when the weight quality of the fake coin is not known ahead of time, we understand that such luck cannot last forever. And most of the time, even if we take, for example, our 12 coin problem that we solved in the previous episode, if we construct any good old adaptive solution, represent that adaptive solution with the corresponding ternary tree, and try to convert that solution, that adaptive solution, into a non-adaptive solution, we will see that we will fail miserably. And in the next segment, we will understand why. If we go back to the adaptive solution of the 12 coin puzzle that we developed in the previous episode and take a look at it again, here it is for your convenience one more time. Then we will see that if we will try to mechanically lift the corresponding LRB encodings from that ternary tree and try to use these encodings as a basis for a non-adaptive solution of the 12 coin problem, then we will fail miserably, and it is instructive to understand why. The answer to that question comes to us courtesy of the space-time problem-solving approach, because in this case, that problem-solving approach tells us that an interesting pairing of the main components of that 12 coin problem is the following one: same time, distinct spaces. That is, let us try to step away a little bit from all the problems that we have been dealing with and think about these problems in general. What are we doing in each and every specific weighing in these problems? In these problems, with each and every specific weighing, we're putting the same number of coins for a given weighing on the pens every time. In other words, if X is the number of coins that goes into one pen, then precisely X is the number of coins that goes onto the remaining pen. And we already saw with the 18 coin problem that that number of coins does not have to be the same throughout all the weighings and throughout the entire experiment. For example, in that 18 coin problem, we saw that in weighing 1, we went 6 and 6. For the weighing number 2, we went 6 and 6. But for the weighing number 3, we went 9 and 9. However, within each specific weighing, the number of coins that went onto the left and onto the right pen was exactly the same. Some students will say, well, duh, this is obvious. However, just like it may be obvious what is going on with the space-time problem-solving approach, here with that observation, sometimes some students fail to make it, and consequently they fail to convert that obvious observation into an actionable algebra. And how can we do that? Well, we convert that obvious observation into an actionable algebra by saying that in the context of our LRB encodings of the coins, the number of the letters L in the kth position in such an encoding must be equal to the number of the letters R in the same kth position throughout all the positions, throughout all the chosen encodings. We can even capture this requirement as follows. Let's say we will write it down as the number of the letters L in the kth position. The number of the letters L in the kth position must be equal to the number of the letters R in the same kth position, where k varies as 1, 2, 3, and so on. And usually the challenge comes from the following fact. If we take the entire set of, let's say, 3 permutations with repetitions of our distinct letters LRB, each of which is available in an infinite supply, then due to the mechanics of the construction of such a set of all 3 permutations, it is evident that that requirement will be met. And we can agree to name such a requirement, or we can agree to name the subset of all the relevant permutations with repetitions that satisfy that requirement as LR balanced. However, the challenge is when the number of coins is not a perfect power of 3, and if the weight quality of the fake coin is not known ahead of time, then the entire set is obviously not going to work, and the challenge is to select only those encodings that form precisely an LR balanced subset. And now we understand why, in some sense, we got lucky with the 27 coin problem, and why we, in some sense, again got lucky with the 18 coin problem. In the first case, like we observed earlier, in the 27 coin problem, we generated the entire set, all 27 3 permutations with repetitions, blah, blah, blah. And obviously, such a set will be LR balanced due to the mechanics of how it was constructed. The number of letters L in the first position in these encodings is equal to the number of the letters R in the first position in these encodings, and so on for all the positions. Likewise, in the 18 coin problem, in some sense, we got lucky that after we removed 9 corresponding encodings, we were still left with an LR balanced subset. And again, the fact that the subset is LR balanced is captured over here on your right. You can go over it one more time and prove to yourself that no matter which position we pick, for example, let's say we pick position number 2 over here, count the number of the letters L in that position throughout all these encodings. And that number will be equal to the number of the letters R in the second position throughout all the encodings. And it is important to understand that the LR balanced subset, the requirement for the subset to be LR balanced, must hold for all the positions, not just one position, but all the positions in the chosen encoding. And if, now that we understand what is going on and why we failed with the 12 coin problem, it is possible to take the corresponding 24 LRB encodings that relate to the 12 coin puzzle, 12 coin problem, and arrange these encodings into the LR balanced subset. In a few seconds, I will show you several pictures or several images that I prepared with the free software called GeoGebra. In the first such image that will be coming up in a few seconds, you will see two encodings. One encoding will be on your left and the other encoding will be on your right. Each such encoding will consist of two columns. The leftmost column will be shown in orange and the rightmost column in each encoding will be shown in violet. The encoding that you will see on your left will be under the LR balanced heading, and the encoding that you will see on your right will be under the non-LR balanced heading. And from that observation, it follows that if we will try to use the right encoding, the encoding that you will see in a few seconds on your right, then we will not be able to use the orange. In both cases, we use the orange column for the corresponding non-adaptive solution, but from the right encoding that you will see on your right, we will not be able to take the orange column and generate a non-adaptive solution of the 12-coin problem from it. However, we will be able to generate an adaptive solution of the 12-coin problem with the corresponding ternary tree. Please take a look. One more time, if you take the 12 origin codings that you saw on your right under the heading not LR balanced, then these 12 origin codings cannot be used in order to construct the respective non-adaptive solution of the 12-coin problem, but these 12 encodings can be converted into an adaptive solution of that problem that can be faithfully represented with the corresponding ternary tree. In contrast, if you go back to the image that I just showed and grab the 12 orange encodings that were shown on your left under the LR balanced heading, then these 12 orange encodings will actually work both ways. They can be used for a mechanical construction of the respective non-adaptive solution of the 12-coin problem, and at the same time they can be flipped into the adaptive solution of that problem that can be faithfully represented with the corresponding ternary tree, and that ternary tree and the non-adaptive solution of the problem that's shown underneath it, they work both ways again, which means that the LRB encodings that you saw on the ternary tree can be mechanically lifted and plopped on top of the non-adaptive solution of the 12-coin problem, and conversely, you can take the orange encodings that correspond to the non-adaptive solution and convert that non-adaptive solution into the adaptive ternary tree based solution of that problem. Please take a look how. The interesting question now is the following one. Is all lost with the origin codings that you saw on your right under the not LR balanced heading? And the answer here is, amazingly enough, no, not all is lost. And if we somewhat creatively hash these 12 orange encodings with the 12 violet encodings that you saw on your right, then it is possible to construct 12 orange LR balanced encodings, and these encodings will be shown in the image right here. Precisely because the 12 new origin codings that you saw on your right are now LR balanced, these 12 origin codings can be used both ways in order to construct a corresponding non-adaptive solution of the 12-coin problem, and these same encodings can be used in order to generate an adaptive ternary tree based solution of the problem. And again, both objects that you will see in a moment enjoy the same symbiotic relationship. That is, from the LRB encodings that can be generated off of the tree that you will see in a moment, we can generate the corresponding non-adaptive solution of the 12-coin problem, and conversely, we can flip the non-adaptive solution of the 12-coin problem that you will see at the bottom into the corresponding adaptive ternary tree based solution of the problem. Please take a look. Before we wrap up this episode, two more things. One, it is a good idea to compare the space requirement for the adaptive tree-based solution of a fake coin detection problem and its non-adaptive counterpart. The adaptive ternary tree-based solution of our fake coin detection problems is very voluminous, but it is very straightforward to read, straightforward to grasp, comprehend, and understand, even though it takes a lot of space. And the non-adaptive solution of the fake coin detection problem is very concise. It takes very little space, but on the other hand, it's quite mysterious because we are totally in the loss of how on earth this solution was generated to begin with. Number two, we have good reasons to think that there exist one or several theorems that connect the adaptive ternary tree based solutions of the fake coin detection problems with their non-adaptive counterparts, and conversely. In other words, we have fairly good reasons to think that there exists one or several theorems which spell out the conditions of if and when, and if we're lucky, even how an adaptive ternary tree based solution of a fake coin detection problem can be flipped into the non-adaptive counterpart. And conversely, we think we have several good reasons to think that there exists one or several theorems which specify the conditions of if and when, and if we're lucky, even how a non-adaptive solution of a fake coin detection problem can be flipped into the corresponding adaptive ternary tree based solution. Why do we think that these theorems may exist? Well, we pretty much proved or demonstrated why such a theory may be true in case of the 27 coin problem and in case of the 18 coin problem. And yes, these are toy cases when the number of coins is a perfect power of 3, when the weight quality of the fake coin is known ahead of time. These are straightforward cases, but this is precisely how the mathematical research works. We begin with something that possesses a lot or heavy requirements, and then we carefully begin to prove that evident theorem with a lot of heavy requirements. During the process of generating a proof for this heavy requirement theorems, we develop a better understanding of what's going on, and then we begin to carefully strip away the heaviness of this requirement until we strip what's going on in this problem to its bare bones, and we look at the essence of what is going on in a given situation. Also, we have good reasons to think that the converse theorem or several theorems exist, because again, let's take a look even at our 18 coin toy problem over here. Well, the weighing number 1 can be flipped into the corresponding adaptive solution that is based on a faithful representation by a ternary tree verbatim. We simply take the coins listed for the left pen, plop them on the left pen. We take the coins listed for the right pen, plop them on the right pen. The coins that are not listed or listed explicitly to be on the table, we throw them on the table. Game over. And for example, for the last weighing, we know that on the last weighing on properly functioning set of pen scales, we can have no more than 3 suspects, And consequently, in this case, for example, on the left pane, we see the coins 1, 3, 5, 7, 9, and so on. And where do we see them here on the ternary tree representation? Well, here is one coin named 1 on the left pane. The next guy is 3. Where is 3? Here. Here is the coin named 3, destined for the left pen. 5 is here. Where is 7? 7 is right here, left pen, and so on. Likewise, for the right pen, we have the even numbered coins, and again, here each coin goes onto each separate pen because precisely we have at most 3 candidates to sort out. So where is the guy named 2? So here it is, coin named 2 on the right pen. The next one is 4. Here is 4 on the right pen. 6. Where is 6? 6 is right here. And for example, 8 is here, 10 is here. Where is 12? 12 is here, and so on. And if you care about these problems more than I do, and if you decide to research this topic further and you prove and publish these theorems, then please be courteous, give some credit to me. And if you prove that this is just a pile of nonsense, then you can blame the Russian guy. Going back to the previous segment just for a second, it feels like there exists a interesting secret sauce within the structure of the ternary trees that represent an adaptive solution of the fake coin detection problem. And again, it feels that this secret sauce may help us flip back and forth between the adaptive and non-adaptive solutions of the fake coin detection problems. Because if you go back and look at the ternary trees that represent the adaptive solutions of the 12 coin problem, you will see that all these trees possess one and the same property, judging by the position of the leaf nodes and the solution coins in these trees. These trees are symmetrical with respect to the perceived vertical, and as they commonly say, symmetry is the first-class citizen of the theory of groups. In any case, the next challenge, the mathematical problem S2M16, will be optional. If you do not like it, or if you do not want to deal with it, feel free to skip the next episode and go to the next episodes in our sequence. But for the curious travelers, we suggest that they try their hand in putting together a fake coin detection problem. It doesn't have to be complicated. Keep it simple. Keep it around a very small and manageable number of coins. Don't make it too complicated. But try to put together a fake coin detection problem that admits a geometric solution. Geometric solution. Think about it. In season 1, episode 2, we described how to practice mathematics correctly. If you cannot solve this problem completely and on your own, then just look at our hints. And here is some hints for curious travelers. For example, think about in the context of the space-time problem-solving approach, which tells us that under all classical physics conditions and one exotic special theory of relativity condition, we have 4 interesting pairings between the space and some other components in the problem. Think about, for example, what can you say about 2 parallel straight lines? What do these straight lines represent? Well, again, because I have the background in theoretical physics, so maybe I'm biased towards thinking like a physicist, but in Euclidean geometry, in the absence of the so-called point at infinity, the parallel straight lines never intersect. And these 2 straight parallel lines represent what? At the same time, they represent 2 distinct spaces. For example, if we imagine a point on one straight line running this way and a point on the other straight line running this way, can it ever so happen under the conditions that I specified that these 2 points will meet? No, it cannot happen. But what if we add another coplanar, of course, 3rd straight line that is not parallel to either one? Well, again, if we make a point, take a point on that 3rd straight line, make it carefully run in this direction, that it can so happen that, for example, here or here, the 2 corresponding points will meet, and what does this event represent? Same time, same space. So something interesting may happen at the intersection of two straight lines, and it is your mission, should you choose to accept it, is to construct a problem that admits a geometric solution where the space-time problem-solving approach exactly juggles the interesting components in it. Good luck. This is it for this episode. Thank you for your time. Thank you for watching. I will see you in the next episode, in which I will discuss the possible solutions of the mathematical problem S2E13.